Exercise 1.2, question 1. Express each number, the numbers that you see in these parts, as a product of its prime factors. That means you have to prime factorize these numbers. Now, what you need to know is, according to the fundamental theorem of arithmetic, every composite number in the world can be expressed as a product of primes, that means can be factorized, and this factorization is unique apart from the order in which the prime factors occur. What that means is, if say two of you, person A and person B, both of them start and try to prime factorize the number 10, then one person might say it is 2 times 5. The other person might say no, it is 5 times 2. Now, is any one of them wrong here? No, both of them are correct because both of them have used the same prime factors 2 and 5, just that the order in which they have written this is different. So the prime factorization itself has to be unique. Nobody else, if somebody says no, 10 is equal to 2 times 3, then that person is wrong because he's used the wrong prime factor here. So the prime factors have always to be 2 and 5 when you're talking about 10, but the order does not matter. This is what the fundamental theorem of arithmetic says. Now it says you can do this for every composite number. So there's no composite number that you'll have, oh, I just cannot prime factorize this. That means each of the parts that we have here, we will be able to prime factorize them. What we will use is the factor tree that you must already be aware of to prime factorize these numbers. Since this is based on what you learned in junior classes, we will not spend a ton of time on this. So let's just get started. The first number here is 140. Now just for a refresher, I'm going to do this nice and slow. 140 is divisible by 2. So 2 is a prime factor. Why? Because 140 is an even number. Now 2 times 70 is 140. Then 2 is already a prime factor, a prime number, so you try to break 70 down. 70 again, because it's an even number, it will have 2 as a factor, and then the other factor will be 35 because 2 times 35 is 70. Now 35 is not an even number, so you will no longer have a 2. So you have to look for the next one. What about 3? 35 is not divisible by 3 either, because according to the divisibility test of 3, the sum of the digits has to be divisible by 3. Now 3 plus 5 is 8, which is not divisible, and also this is a very small number, so you know you cannot divide this by 3. Next prime number would be 5, and it works perfectly there. Now since 5 times 7 is 35, that becomes your other prime factor, the other prime number. Now you cannot break any of these down further. It's all completely broken down. So the prime factors that this number has are these that you have at the last stage in every branch. So these are all the prime factors. So if I express this, it is 2 to the power 2 because I have 2 of them. Here's 1, here's 2 times 5 times 7. Let's move to the next part. 156. Now 156 is an even number, so it will have a 2, and the other number would be 2 is 2 multiplied by what will give you 156. Or you can think 156 divided by 2 will be how much? Now when you do this division, you will get 78. Now 78 again is an even number, so you will have 2. The other number will be 39 because 2 times 39 is 78. Now this is not an even number, so no more are you going to have a 2, but this is divisible by 3 because 3 times 13 is 39. Now all the numbers that we have at this stage are prime numbers, so we cannot break any of them further. So when we write the prime factorization, it is 2 squared again because you again have 2 of them times 3 times 13. Let's go to part 3. 3825. Now this is an odd number, so I don't even have to think about a 2. But you know what? I will not check for 3. Why? Because I can already see that the last digit is 5. So I'm sure that this is divisible by 5. And 5 is a prime number. So I'll start straight with 5. Now what is the number that I'll write here? It is 3825 divided by 5. When you do that division, you get 765. Yet again, this ends with a 5, so this is again divisible by 5. When you further divide this by 5, 765 by 5, you will get 153. Now the last digit is not 5, so that trick will not work anymore. It is still not an even number, so we're still not thinking about 2. Well, once if it's not an even number in the beginning, this big number, the factors can never be even. Now let's think about 3. Is it divisible by 3? Well, if you add and see the digits, the sum of the digits is 1 and 5 and 3, that's 9, which is divisible by 3. So the whole thing will also be divisible by 3 and the other number would be 51. Now when you break 51, it will be 3 times 17. This is now the stage where all of them are prime numbers. Each branch ends with a prime number. So let's write down the prime factorization. You have 5 squared times 3 squared times 17. Now somebody might begin with the 3's and then go to the 5's. Even then the prime factorization will be the same. You know that the order does not matter. Just that your prime factors have to be the same. Let's go on. Okay, here is the prime factorization for 5005. The numbers that first came to my mind, I used them. Your order could be anything, remember, but your prime factorization will still be counted correct. Make sure you do this and check that you get the same prime factorization. I'm going to do the same for part 5 now. Please pause the video and try that yourself and then see that your answer matches mine. There you go. Now, this time, if you tried, you might have realized that the numbers were not that easy to find because you did not have any prime factors till the number 17. So, it was a lot of numbers to check till you get to 17. A lot of people get disheartened and might just conclude, oh, this is just a prime number and will not have any prime factors itself. But you need patience for some weird numbers. They have prime factors, but you have to also know when to give up on checking, when to just conclude that it is a prime number. But that is not something we're being taught right now. In a bonus lesson later, if I see enough demand for that, I will create a video to tell you when exactly you need to stop. For now, we were learning prime factorization and we've done that.